course.
Okay. Okay, without further ado, you may start your presentation now, please.
Yeah, thank you. In this opportunity, I will present our result of flame spray chromium carbide nickel chromium coating on A516 cell. Okay, global warming is our problem in the world. It's due to the greenhouse gas emissions such as carbon dioxide. Indonesia supply almost 2% of carbon dioxide gas emission in the world. And most of the greenhouse gas emission come from energy. Whereas in energy sector, about 76% use coal and fuel. It is well known that coal is not energy and non-carbon neutral resource. Due to that situation, the government make policy which in 2040 Asia will stop coal-fired power plant application. Biomass is generally considered as a carbon neutral renewable energy resource for replacing fossil fuel energy. However, in biomass fuel fossil energy, hot corrosion induced by alkaline chloride a serious problem. Some detrimental elements such as sulfur, biomass forms hydrochloric or alkaline chlorides such as potassium chloride and natrium chloride. And due to cooling boiler exhaust gases, chloride condenses and forms salt. This corrosion called chloride-induced active corrosion. This corrosion is detrimental to many elements such as nickel, chromium, aluminum, molybdenum, etc. And corrosion in boiler can also occur due to liquid. The most destruction corrosion in biomass boilers is molten salt. So the problem in co-firing biomass and power plant is chloride-induced corrosion. Coating is the most economical, easy, and efficient problem solution. Common substrate that used in boiler power plant is low carbon steel. It is due to low carbon steel is not too brittle and has good performance in manufacturing. Material for coating which has good performance in chloride environment is nickel. It is due to nickel has the biggest value of gives energy than other elements when react to chloride. In the coating system, the excellent coating will produce protective oxide scale. And this figure presents that some protective oxides such as chromium, silicon oxide, and then aluminum oxide are stable for the protective oxide scale. However, in chloride environment, alumina scale causes spallation of the layer. Thus, chromium is the best element for reducing the oxide scale in chloride environment. And then chromium carbide coating have been used for high temperature application, heat exchanger, and biomass fuel fire boiler, and etc. The coefficient of thermal expansion of chromium carbide is nearly similar to nickel and iron, and it will minimize residual stresses generated during coating deposition, and also can significantly modify the thermal cycling life, spallation resistance, and fatigue performance. Thermal spray emerged as one of the best methods for develop coating that can be used in high temperature corrosion and wear application. And flame spray is an energy to operate, and the cost effective compared with other thermal spray technique. However, there are few studies available which studied the corrosion behavior and molten salt condition in flame spray coating. In this present study, carry out deposition using this technique. And next slide will present methodology. First is sample preparation. We used low carbon steel for substrate, and then chromium carbide nickel chromium for material coating. And the next step is deposition process. Before do deposition process by flame spray, we do blasting in the sample. And the next is corrosion test. Corrosion test used paper salt corrosion furnace. The hot corrosion of chromium carbide nickel chromium coating were investigated in molten salt. There are natrium chloride and then potassium chloride at 600 degrees Celsius for 100 hours. And the last step is characterization using XRD and then scanning electron microscopy. Scanning electron microscope equipped energy dispersed X-ray. And then this is the result. The first figure shows the surface morphologies of the sample. This figure showed surface morphology at different exposure duration from 0 hours until 100 hours. Cracking and spallation were observed in uncoated and coated substrate. However, on uncoated substrate, there were observed more cracking and spallation in all of the specimen faces. We can look for the figure that all of the faces of specimen have spallation. The chromium carbide nickel chromium coating deposited by flame spray process on low carbon steel behave more protective than uncoated steel. The mirror spalling observed at the edge of the uncoated specimen. And the next figure shows the mass change of uncoated and coated specimen. Mass change show that chromium carbide nickel chromium coating had the bigger value than uncoated specimen. It was due to the spallation more observed on uncoated specimen, whereas mass change on chromium carbide nickel chromium coating showed the spallation of observed after 80 hours. You can look from the figure that there were decrement on this area. Next result show surface morphology as coated specimen and uncoated specimen. It observed from as coated specimen in this figure. There were some melted particle and then some partially melted and melted particle, unmelted and melted particle. And also observed crack, micro crack in here. And then from this EDR spectrum, we can identify that the element composition in this particle is nickel chromium oxide, nickel chromium and oxygen. And next figure show uncoated specimen after corrosion test for 100 hours. From this figure, we can know that there were two shapes in this morphology. First labeled by A and then second labeled by B. A shape is called a self-oriented flower that contain ferrum and oxygen. And then the next shape is B that contain ferrum and oxygen too. And the next figure is chromium carbide nickel chromium after corrosion 100 hours. They also observed two shape in here. That the one shape is distorted cube. In this distorted cube, there were some elements such as nickel, chromium, and oxygen, and then and this area, there are much of chromium and oxygen. And then next is cross-section micrograph of X-ray specimen. The coating presents some pores. We can see on this picture some pores and then micro cracks also detected in here. The coating thickness for about 200 micrometer, and it was clearly recognized that the coating consisted of lamellae elongated in direction parallel to coating surface. In this area, detected or observed carbide particle were distributed in coating evenly. Microcarbide particle is in angular shape were observed in coating. Next is XRG pattern in X-ray specimen and then coated and uncoated specimen after corrosion 100 hours. From the X-ray specimen, the chromium oxide peaks were observed in coating due to the fabrication of lens wave. It was related to EDS analysis, which on surface and cross-section specimen observed oxygen. And it was indicated that oxidation can occur due to the oxygen gas usage. The other phases were detected in coating, such as CR3, C2, and then CR7, C3, and CR23 and C6. Under high thermal input during flame spray process, chromium carbide with composition CR3, C2 led to formation of CR7, C3, and CR23, C4, C6, as reported in previous study by Lu in 2020. And uncoated specimen after corrosion 1 hours. They were observed ferrum oxide, which is unprotective oxide. So the last is chromium carbide nickel chromium coated specimen after 1 hour corrosion. That it was observed chromium oxide 2 and then nickel chromium oxygen spinel. Chromium oxide and nickel chromium oxygen spinel is arm protective oxide, and from here it still detected chromium carbide and 3 kinds of chromium carbide. Specimen after 1 hour corrosion were not observed chlorine, potassium, and natrium due to phases were evaporated during exposure to corrosion. And this is the mechanism of corrosion. First is coated specimen, and then this is uncoated specimen. Compound containing chloride react with alloying element such as chromium oxide, and then chlorine is able to penetrate and damage metal oxide through gaps, if there were any gaps. Next, make the formation of metal chloride, and the next step is will evaporate if the temperature above 400 degrees Celsius. And the last step is oxide formation, and will lead to oxide breaking and spallation. So for carbon steel substrate, the mechanism of corrosion, there were 3 layers of ferrum oxide, and also potassium chloride and natrium chloride were evaporated during exposure of corrosion. So this is the conclusion in our research paper. First, chromium carbide nickel chloride coating was successfully deposited on A516 by flame spray process. Some pores and a few microcrack observed on spray coating, and then metastable chromium CR3, C2, and CR7, C3, and also stable CR23, C6 phases were observed on spray and corroded coating specimen. And the last is the chromium carbide nickel chloride coating shows the protective oxide such as chromia and nickel chromium oxygen spinel. Although uncoated specimen observed unprotective ferrum oxide, so that will make the spallation which observed on specimen after corrosion. And thank you for the attention. It will be a pleasure for me if there were any suggestion for me, and I return to the moderator. Thank you.
Thank you, Bu Safitri, for a great presentation about the flame spray method to coat the steel with the chromium, carbon, nickel, chromium. I would like to give an opportunity to the participant to ask questions. So if there is anyone to ask, please raise your hands or write your question in the chat box. Maybe one question. Okay, no question from the participants. So maybe I would like to ask one question. So, Bu Safitri, what's the challenge in the flame spray coating method to coat the steel with this chromium, carbon, nickel, chromium? Or maybe the simplified question is, what's the disadvantage of using this method that need to be overcome for its implementation in industrial scale?
Okay, thank you for the question. I think for flame spray method, that was a conventional technique, but it still used in many application because of easy to use and then cost effectively. But the challenging for this flame spray method is they were uh, observed some pores that unwanted unwanted areas of course for the coating. So yeah, I think maybe the porosity is more much than the other technique in thermal spray technique.
Okay.
Okay.
Thank you, Bu Safitri, for great answer. So unfortunately, we have a very limited time. So thank you, Bu Safitri, for your presentation. And then we'll move to the next invited speaker. It would be Mr. Joko Hadi Prayitno, or maybe Feby Merita from the ICAMT, National Research and Innovation Agency, or BRAIN Indonesia. Are you with us, Ms. Bu Feby? Hello? Or maybe Pak Joko Prayitno? Okay, no. Okay, maybe we can move to the next oral speaker. Mr. Hamonangan from the National Research and Innovation Agency, Indonesia. Are you with us?
Yes. Okay.
Okay, please start your presentation.
Okay. Thank you very much for this opportunity, dear estimate committee, moderator, and fellow participant of this conference ISM 2021. We have to present our paper here with the title of Development of Polyurethane Coated Aluminum Powder Using Solvent Evaporation Induced Method. Okay, we are from research organization in aeronautics and space from Rocket Technology Center. Yep, this is the contributors from Laboratory of Energetic Material. Okay. Then let's continue to introduction. The first is the use of aluminum powder in this industry of propellant explosive and pyrotechnics. The addition of aluminum will improve the specific input of performance up to 15%, but it can tends to form agglomerates, which result in decrease in thrust. Using much smaller size, for example, the nanoscale aluminum powder reduce the size of agglomerates, but it bringing in a new problems. This is the view image for sample of our works. This is the aluminum composite propellant. With the high viscosity slurry, it is very hard to cast and cure. And this is the sample of the pure edging and mechanical performance of the propellants with the previously high aluminum content. In our laboratory, we use two types of uncoated aluminum powder for the propellant formulation. Analyze the purity. It's high purity grade of 99.8655% to 99.8699%. It's not uniformly safe. is highly irregular and is porous. This is the previous works we have done, the particle size difference and the size distribution. Okay, this is the same image of uncoated aluminum powder that we use in propellant formulation. Yep. Next, in the HTPB binder, the PU base, hydroxy terminated polybutadiene is the polymeric binder. Cured with the isocyanate substance such as TDI, toluene diisocyanate, or EPDI, isoporon diisocyanate. Okay, the HTPB we use had been analyzed to have microstructure composition of 1.4, which is about 12.99%, vinyl 52.54%, trans 34.77%. This is the illustration of the polymeric chain of HTPB cured by IPDI. Yeah, it brings to another topics we have pursued to address the problems. The coated aluminum powders. The coated aluminum powders could prevent the agglomeration of aluminum particles. The problems of high surface area of the nanoscale could be prevented by using coated particles. The focus of research in coating materials are metallics or polymeric-based coating. Metallic coating such as nickel-coated aluminum powders, while the polymeric-based is PTFE, polytetrafluoroethylene coated aluminum powders. The coating did improve the stability of materials, make it less sensitive, shock resistant, so it is much more safer to transport and to use. Then we have come to the question, since we use the polymeric binder of HTPB as the framework for the composite propellant, why not using the same polymers to coat the aluminum powders? Okay, the PU polyurethane coated aluminum powders. Using the same polymeric substance for aluminum powders coating such as the propellant binder offers a favorable effect in particle dispersity. We can use the like expression. Previous attempt to produce PU coated powders was done by N et al., which produced the PU coated RDX powder for propellant production. The method employed by N et al. Can be used with slight modification to produce PU coated aluminum powders. This is the samples of the coated powders coated with polyurethane. Next, the methodology, material and equipment, materials such as this, uncoated aluminum powders, two versions, L1 and L2, HTPB, TDI, and ethyl acetate. Equipments with vacuum distillation apparatus, SEM, from Penhamwood Pro XT Stop, and FGER, from Shimatsu ER Prestige. Is the equipment. We actually build this with the available materials, equipment in our laboratory. This is the vacuum distillation apparatus. Yep. Then the same image characterization were carried out by ImageG and Penham Pro Suite software. Okay, next the fabrication. Software operation in this method. Okay, this is here. The PU solution programs of HTPB and TDI in ethyl acetate, 50 milliliters, with the L2 aluminum powders 200 grams in solid liquid mixture, combined to form solid liquid mixture. Then we vacuum distillation it at 60 degrees Celsius, and the ethyl solvent was removed. We produce aluminum powder PU mixtures which is still wet, that need to be cured in oven at 60 degrees Celsius for 1 week. And we produce the PU coated aluminum powders, which have to be sieved before ready to use. We also explore the mixing sequence variation in here. We perform the variation of mixing sequence to see if there will be differences in the property of PU coated aluminum powders. The mix sequence is liquid pour and solid addition. The liquid pour is we pour the liquid into the solid of aluminum powders, and we have aluminum mixture which we have to stir vigorously to form stable mixtures. Okay. If there any difference both by the size and shape difference of aluminum powders in coating result, we produce the PU coated AL1 using the liquid pour coating sequence. And this is the another coating sequence. When the solid addition coating sequence, solid is added to the liquid, the PU solution, and then stir it to get the stable mixtures. Okay. Next is the results and discussion. The first is PUL coated particles sand characterization. As you can see here, this is the same image of the coated particles. The A is Al2 PU coated. The smaller size with precursor we use is about 11 microns in size. So it forms like this, the PU coated liquid poured, and the B is the solid added with the same Al2, and the C is the Al1, which the precursor is about 33 microns. This is the coated liquid poured method, the same image. Next. As you can see here, the difference in the sequence, coating sequence, did bring us quite a few differences here. We found interesting result with the solid added have a slightly smaller in size, in particle size, slightly higher in circularity and roundness, and also in aspect ratio, while the solidity is slightly lower. Then this is the PUL1 liquid pour. It turns to 12.1 microns, previously 33 to 12.1. The circularity is also improved, solidity and roundness improved, while the aspect ratio is reduced. Coated powder is smaller in size than the uncoated particles, more spherical shape, look like less porosity compared to the uncoated aluminum powders, and the surface is smooth and clean. Why is it happening when the uncoated particles larger in size compared to the coated one? It's about the homogenization effect here. The solid with water, dissolve salt into the water, it is smaller in the liquid phase. In the solution, Oh, I'm sorry, there is technical difficulties. Can I continue?
Yes, continue. Maybe 2 more minutes.
Okay. Okay. Here's the comparison in size. It's about 58 to 64% in terms of size reduction when using the ethyl acetate. Okay, and this is the FTER characterization. It shows different peaks compared to uncoated ones. And that can be used as indicator 70 here, and this is the uncoated particles FTER spectra. Okay, there is so much differences compared to uncoated ones. This is PUL1 coated version, and this PUL2 liquid pore, and this PUL2 solid eddy. Okay, as here is the comparison. The peak transmittances, we use the 1.4 cheese, 1 ml. The trans is all detected, so it can be used as indicator that PU layer is successfully formed to cover the aluminum particles. Okay, the conclusion here, the soap evaporation methods using ethyl acetate can be employed to form the compacted, highly spherical PU-coated aluminum powders and smaller in size with 58 to 64% in size reduction compared to uncoated particle due to homogenization effect when dispersed in ethyl acetate. The PU coating layers formed by two variations of coating sequence, so clean and smooth surface with the solid addition coating sequence proven to produce smaller and particles, more stable coating layers, and from the FTER we can deduce which more stronger the solid addition is produce the stronger absorption peak. So we can recommend it the solid addition coating sequence over the liquid porous coating sequence to produce smaller coated particles with much better shape characteristic. Okay, thank you very much for the attention and the opportunity. Here's my respondents enter emails, and I will return this opportunity back to moderators. If there is any question, please don't hesitate to ask. Thank you.
Okay, thank you, Mr. Hamonangan, for your nice presentation. So if there's any question from the participant, please raise your hand or write it on the chat box. Okay, if there's no questions, we are very sorry to say that we have very limited time. So we will move to the next speaker. If you have any question, please feel free to contact Mr. Hamonangan privately. So thank you, Mr. Hamonangan, for your presentation.
Yes, thank you. Thank you very much.
Okay. We'll have our next speaker. There's one speaker that cannot attend in this session, so we'll move to the last of our speakers. Ibu Ismudiati from Engineering Physics, Telkom University of Indonesia. Are you with us? Ibu Ismudiati or Indra Feraduan or Indra Wahyudin? Are you with us? Let me see the participant list here. Okay, I think the speaker is not on the list. So maybe it will be the end of our sessions. Okay. Oh, maybe I will give 2 minutes for the committee to contact the last speaker. Okay, I have information from the committee that our last speaker also cannot attend in this session. So we will end this session and I will give the lead of this room to the PIC, Mr. Rido.
Okay, thank you, Mr. Farudin. We will have the appreciation for our moderator. Okay, so this is the certificate of appreciation I will give to Mr. Muhammad Farudin, Bachelor of Engineering, as a distinguished moderator in International Conference on Advanced Material and Technology on December 14, 2021. On behalf of the founder of NBRI, Professor Dr. Ernad Evi Kartini, and the co-founder, Professor Alan J. Drew. So once again, thank you for your time being the moderator.
Thank you, Mr. Rido. Thank you, NBRI, for inviting me. Thank you.
So is there any speech from Professor Evi?
Ada.
To Professor Evi, do you want to give some speech to Mr. Farudin?
Wait a minute, Mr. Rido. We have our speakers here, so he will join soon.
Okay, then I will give the floor back to Mr. Farudin again. Thank you.
Oh, sorry. Okay, we'll move to the last speaker. Is it Ibu Nuning or Ibu Ismudiati?
It must be Ibu Nuning, Mr.
Oh,
Farudin.
Ibu Nuning. Okay. Ibu Nuning, are you with us?
And I think it's still on the waiting room.
Oh, yes.
We will send it as soon as possible, Mr. Farudin. So sorry for this.
Okay. Okay, maybe we still have more time for the discussion for Mr. Hamonangan. Are you still with us? Oh, no.
Yes.
Okay. If there's any question from the participant, please delay for your question directly, or maybe you can write your question on the chat box. Okay, well, if there's no any question, wait a minute. Okay, maybe I will ask Mr. Hamonangan.
Yeah.
So, what's the advantage and the disadvantage of the using of polyurethane to coat the aluminum? Maybe you
Okay.
can give more explanation to us.
Okay. As you can see before, the problems we encounter. Can I share screen again?
Yes, please.
Okay. Let's see. Yeah. The problem using the high solid content aluminum, we use about 18% aluminum in our products. We encounter the slurry. The propellant slurry is in hard to cast, and it's unreliable. It's hard to cure. The viscosity is so high. We encounter about 12,000 poise, which is problematic to cast and use in the methods of the gas bonded propellant production. The other end is you can find the pure propellant have a very pure have a very pure aging and mechanical performance. As you can see here in this image, which the third image I shared, it is about 2 months before after the propellant was fully cured and removed from the cast. There is already a hole in here, 2 holes to be exact, which the structure is crumbling. We have already analyzed this with X-ray scanner, and we found the aluminum agglomerates here with different concentration and different distribution in these propellants, which is if the aluminum can disperse better in these propellants of the matrix is STPB, it's polyurethane base with the same surface profile and as the STPB itself, it can disperse better. And we already tried and create one propellant here, which the slurry is quite low in viscosity. It's under 500 poise, which is highly favorable in this propellant production. There is one of the advantage when using polyurethane as a coating for the aluminum powders. Hope it will answer your question, Mr. Fakrudin.
Okay. Thank you, Mr. Hamonangan. But please, can you share again the slide number 16, maybe?
Oh yeah, okay. Slide number 16.
It's page 16, maybe.
Okay, yeah.
Okay. So what's the comparison with the bare material, bare aluminum, uncoated aluminum? Is it the particle size is smaller or?
Yes, it's much more smaller. This is the PU coated aluminum particles, and this is, I will say, this is the previously uncoated. As you can see, the particle size, which we make a comparison here, the uncoated of Al2, for example, is 11.105 microns compared to the coated ones of liquid pore. We get 4 microns, 4.65 microns of particles. The solid addition method, we got 4.45% microns. I'm sorry. You can expect a size reduction from 58.24% to 60.4%, 0.4% when using the Al2 to produce the coated aluminum, PU coated aluminum powders here. The size reduction is quite large here, from 58 to 60%. And the others, as you can see here, the circularity, the shape characteristic, the circularity, the solidity, the roundness. It get much improvement from here. Yep, as you can see, it's below 0.9, the security, solidity, and roundness here, and it gets here, the security grow to this 0.9, the solidity grow up to here, and the roundness also grow up. Here is the solidity, as you can see here in the particles compared to this one. Okay, we can deduce qualitatively that the coated particles have less porosity than the uncoated one. It will help in the aluminum powders distribution in the polyurethane framework of the propellants. Okay, that is the answer.
Yes, thank you for your detailed explanation. And I think that's all for the presentation. Thank you once again, Mr. Hamonangan.
Yes, thank you. You're welcome.
So yes, thank you. So we have our last speaker here. It will be Mr. Seto Roseno. Are you with us? Mr. Seto? Can you unmute your microphone? Okay, maybe there is some problem with the connection. Okay.
Okay.
Hello, Mr. Seto. can you unmute your microphone?
Okay. Yes. Thank you very much.
Yeah, thank you. So, without further ado, please start your presentation, please.
Okay, thank you very much, Mr. Moderator. Please allow me to introduce myself. My name is Seto Roseno. I'm from Technology Center for Materials at the National Research and Innovation Agency. At the moment, I would like to present our paper with title Publication and Characterization of Glass Fiber and Polymer Composite Skins. I'd like to share my screen first. Okay, yes. The objective of this research is to investigate the properties of the different glass fiber and polymer skins that are made of the two types of thermoset resin, which are reinforced with glass fiber. They have been fabricated by two stages of manufacturing techniques that lay up, followed by the vacuum bagging techniques. And the procedure that we impose in this research is the first we mix the two constituent materials that made up our composite, the glass fibers and the resin, which are being hand laid up, and then the next step with the vacuum bagging, and then as the subsequent step is to characterize the resulting materials being fabricated with the three types of characterization techniques, which include the optical microscope observation, thermal analysis, and mechanical behavior properties, which compose of two major properties that are tensile and flexural strength. So basically, we developed the two glass fiber reinforced plastic using two types of matrix materials. First is epoxy materials. The second one is derived from the saturated polyester. And from the optical microscopy, we see a result from the one that is composed of the glass fiber reinforced polymer, which is based on the epoxy resins, with the average GFRV epoxy fiber diameter of around 48.6 micrometer. And it was found that relatively uneven resin distribution. However, when we have the glass fiber reinforced polymer, which use unsaturated polyester, we found no dark spot, which corresponds to a relatively small void detected. In this case, the average glass fiber reinforced polymer using the unsaturated polymer fiber has a diameter of 22 micrometer. So here we understand that there is a resin sink rates, which found bigger when we use the unsaturated polyester resin compared to the epoxy matrix material. From the thermal analysis, we found that the glass fiber is thermally stable at the test temperature that we employed from 0 up to around 350 degrees, and there's been two-stage decomposition involved when we apply this test. First, mass loss due to water and other impurities in the range of 50 to 265 degrees Celsius, followed subsequently with the second mass loss due to cured resin degradation, found in the temperature range of between 275 up to 550 degrees Celsius. finally, when we test our specimen in light of to understand the mechanical response of the materials, we apply the tensile test. We found that the sample of GFRP based epoxy based GFRP has tensile strength of 190.9 megapascal compared to the that of the properties of the polyester based glass fiber reinforced plastics, which achieve tensile strength of 240 megapascal. So we look at our previous study when we when we observe from the microscopic analysis that the uneven resin distribution lead to bad resin fiber adhesion, and there is a consequence of having lower strength when we have the materials with epoxy based glass fiber reinforced plastic. From the fractural strength point of view, we have again a lower fractural strength from using the materials of epoxy based glass fiber reinforced plastic compared to higher, significantly bigger fractural strength of the polyester-based, unsaturated polyester-based glass fiber reinforced plastic, having fractural strength of around 265 megapascal. So in the conclusion, we can state that the glass fiber adhesion proved to increase the value of tensile strength and fractural strength properties. However, the glass fiber reinforced plastic using the unsaturated polyester skin has a lower tensile and fractural strength compared to that of the glass fiber reinforced plastic using the epoxy matrix materials. So that will be all for me or for this presentation. Hope it's clear, and I'm more than happy to welcome question and from the audience. Thank you.
Okay, thank you, Mr. Seto, for nice presentation about the fabrication and characterization of glass fiber GFRP. So we move to the next session, that is question and answer. Is there any question from the participant? Please raise your hand to ask directly, or write your question on the chat box. Okay, there's no question. Maybe I would like to ask one question. What is the main application of this GFRP material? Because I think there are not many people know about this material, including me. So can you please explain to us?
Yes, thank you for the question. Basically, we have developed different types of glass fiber reinforced plastics used widely in many engineering applications, include the building and components, automotive components, or marine components, or we can also apply this low cost effective composite materials for different consumer products applications, and not only for engineering applications. So we have thought that there's new types of materials, which are very well known for its lightweight structures, high strength to weight ratio, including high corrosion resistance and good weather resistance materials applied for different type of applications that I've mentioned before. But in particular, at this point of time, we actually has done several experiments in order to see the applicability of this material for our current project, that is building earthquake resistant low cost rapid construction building, which are very suitable for this material in in application for its interior building components. So I guess this material can be used and applied there for this type of application. I think that's one of the typical application of this GFRP based composites. Yeah.
Okay. So it's lightweight, high strength, and no less corrosive.
Yeah.
So in current application, is it has been implemented on the building?
Yes, yes, particularly for our development of earthquake resistance permanent house. Yeah. So for its partition or in-wall building or ceiling panels, yeah, or even we can apply this for the floor panel as a floor panels, yeah. But we also plan to see the viability of these materials as the structural frame of the house or the building, because if we look at the current development of the glass fiber reinforced plastic, they also can be applied for the structural components of the buildings or the bridge, yeah, or even other types of application like transportation modes of vehicles, etc. So there are numerous applications for this type of materials, but in particular at the moment we focus on the application for its for the building components. Yeah.
Thank you, Mr. Seto, for your nice explanation.
Yeah, my pleasure.
It's very informative and
you're welcome.
Okay, maybe one more question from the participants. Okay, I think there's no more questions, so maybe we will end this session with the last speaker, or with Mr. Seto as our last speaker. So thank you once again, Mr. Seto, for your participation in this conference.
You're welcome. Thank you.
Thank you. So I will give the lead of this session to Mr. Rido.
Okay, right now we just completed our parallel sessions. Congratulations to all the participants that already presented your topics. After this, we will have a break session until 1:30 p.m. Resume again 15 minutes earlier. Also, we would like to thank MRS Aina, MRS Thailand, and PT Surveyor Indonesia for sponsoring ICAMT 2021. Thank you, and you can leave this breakout room.
Thank you, Mr. Rido. Thank you, everyone.